All right, good morning, grade 7. It was good to see a bunch of you yesterday on Zoom. Nice to see your faces as it's been it's been over 2 months since we've seen each other since the beginning of what was officially March break. All right, for today's lesson, we're going to be talking about combinations. So yesterday we talked about permutations, and that was where order mattered. So you can think of if your mom has 5 different colored popsicles, maybe there's 5 kids in your family. The order matters, right? If you want to get the color you want, you're hoping that you're further up in the line of choosing because then you have the most choice. But if you're the 5th person to choose, you only get what's left. So that's a permutation where the order matters. So let's start with a bit of a review question. So let's say I have 2 extra tickets to a Blue Jays game, and I have 5 friends that would like to come along. Their names are Anne, Bob, Carl, Dave, and Eli. How many different groups of friends can I take? So the important information we have here is that I only have 2 tickets, but I have 5 different friends that are interested in coming along. So what I've actually done here is I've created what we learn to be a sample space, okay, where I've written down all the different groupings or arrangements of my friends. So notice that I conveniently made it that I had the letters A, B, C, D, and E for each of the names of my friends. So here I'm taking Anne and Bob. Another option is to take Anne and Carl, Anne and Dave, and then Anne and Eli. So I created a sample space with all the different possible arrangements of my friends. And you'll notice that I am able to take 4, 8, 12, 16. There are, in fact, 16 different possible arrangements for when I take my friends using my sample space. Now what I want us to do is, before we go on to this problem a bit more, I want to talk a little bit about what I said before, the difference between permutations and combinations. So permutations, which is what we studied yesterday, is when order matters, okay? So if we are voting for a president and a vice president, the order matters. First, I would vote in who I want to be president. Let's say it's of a class. And then my second choice would be the vice president. So if we were voting for someone to be president of our class, and let's say we picked Matthew to be the president of our class, that automatically means that he can't be the vice president, so there are fewer options for vice president. The order matters. Same if we're thinking about who gets first and second place. Let's say for our talent show that Mr. Wurst and I are setting up, first and second matters. If I assign, let's say, Anjali to get first place in the talent show, she can't be second place because she's already first. Okay? Same with determining who will go first in a game. Let's say we're playing, we're playing archery or something like that. Probably the person who goes first has a little bit of an advantage. So order matters in permutations. The order matters. So maybe you can think about the word permutation. You might want to think about the word position. Okay? It starts with the letter P, permutation, position. Now what we're going to talk about today is combinations. With combinations, the order does not matter. So let's just say I needed 2 people for a committee. There were no different jobs in the committee. I just needed 2 people. It doesn't matter the order that I choose those 2 people in. Same with picking 2 class representatives. When you go to high school, they have student council representatives. They're both equal positions. They do the same thing, so it doesn't really matter with the order. Okay, and then my original example with the Blue Jays is similar to this one. Who gets to go to a concert if I only have 2 tickets? Now, let's think carefully about what I said all the way up here. Order does not matter. So now let's go back to my original problem with the Blue Jays game. Now let's think about the fact that order does not matter in this type of an example. So let me just erase this. If I have Anne and Bob going together, A, B, that's exactly the same thing as Bob and Anne going together. The order does not matter. So Anne and Bob and Anne are actually the same combination. So what we want to do is not count Bob and Anne as one of our options. Because whether I say Anne and Bob come with me to the Jays game or Bob and Anne, it's the same thing. Same with if I take Anne and Carl, that's the same as thinking Carl and Anne. So I cross out that one. So what we can see is we actually have a bunch of different pairs going on. Anne and Dave is the same as Dave and Anne. Anne and Eli is the same as, oh, and here's where I realized that I made a mistake. Looks like I forgot to do the E column. I should have EA, EB, EC, and ED, which would also change this to 20. There we go. That's better. Anyways, back to Anne and Eli. This is a repeater. Okay, so I've crossed out all my repeaters so far with all the A's. Then if I have Bob and Carl go, that's the same thing as Carl and Bob. Bob and Dave is the same thing as Dave and Bob. Bob and Eli is the same thing as Eli and Bob. You should kind of see a little bit of a pattern going because I set these up pretty logically. Carl and Dave, same thing as Dave and Carl. Carl and Eli, same thing as Eli and Carl. Then we have Dave and Eli, which is the same thing as Eli and Dave. So what I've actually done is I've gotten rid of any combinations that were the same because order does not matter in this situation. So to reiterate, what I'm saying is that taking Anne and Bob is the same thing as taking Bob and Anne. Okay, so that's why I crossed out Bob and Anne. So what I really only have is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I don't have 20 combinations. I actually only have 10 different combinations of friends that I can take because we're working with combinations where the order does not matter. So this is one way to figure out or to solve a combination question. It's using a sample space, which we're going to call method A. That'll show up in your worksheet for today, method A, sample space. This is what I'm looking for you to do. But there's another way to solve this same question. So I haven't rewritten the question. Let's go over here. But another way to do it is to make an organized list. So what I mean by that is I'm going to start with Anne. And this is outlined in your textbook too on the lesson part. And I'm going to go, well, Anne goes with Bob, Anne goes with Carl, Anne goes with Dave, and then Anne goes with Eli. Then I'm going to go, okay, I've done Anne. She's gone with all the different people. Then I go to the next line, I go Bob. Well, Bob needs to go with Carl, Bob needs to go with Dave, and then Bob needs to go with Eli. I'm done all the possible combinations with Bob because he already was with Anne. Now Carl doesn't need to go with Bob or Anne because we already know that we've done that. Carl goes with Dave, and then Carl goes with Eli. We're done with Carl. Then Dave goes with Eli. We're done with Dave. Then we're also done with Eli because there's no one left for him to go with. And we will see once again that there are 10 different options. So this is making an organized list. It's very similar to what we did before with the sample space. With the sample space is you create all the different combinations and then you cross out the ones the same. This one's a little bit more logical because you're going step by step to think of all the different combinations that there could be. So this is going to be method B, which is the organized list. Okay. All right, let's do one more. I would say that this is the trickiest one to understand. Okay. So just like in our last few lessons where we've drawn tree diagrams and made sample spaces, and at the end we sort of get to a formula or mathematical way to express it. That's what we're going to do here. So the reason this is a little bit tricky is because you need to think a little bit about what options you have. So if I want to figure out how many different combinations I can make, what I do is I start with, well, let me start with all the different permutations that I can make, all the different arrangements. If I want to find that out, I could go, well, this is almost like working with factorials, but not quite. I'm going to say for my first choice of my friend, I have 5 different choices. Then for my second choice, I have 4 different choices. So I can go 5 times 4, which gives me 20 different choices. Okay. But then what I'm going to do is I'm going to divide that whole number by the different amount of arrangements I can make with my two people. And this is where it gets a little bit hard to understand. Don't worry, we'll be doing a lesson with this again on Monday. So if you don't quite get it right away, that's okay. So what we're going to do is we're going to think, well, I'm actually only taking two people. Let's say I have two people. Here are my two boxes for my two people. How many different ways can I arrange those two people where order matters? Well, the different ways that I can do it is actually 2 factorial. And we know that 2 factorial is 2 times 1. So I actually get 20 divided by 2, which is basically getting rid of all my repeats. And my answer is 10. Okay, it's a little bit difficult. Let's try another one with a mathematical expression. So let's say I have 10 different pizza toppings that I can put on my pizza from Domino's. They only have 10 options today, but the deal is that you can only choose 4 toppings. So how many different combinations can you make? So notice we're looking for combinations. It doesn't matter what order I put the toppings on my pizza. It's not a permutation. The order doesn't matter. I can choose whatever I want. But as soon as I choose something, the amount goes down. So I can think of it like this. Well, I have 4 choices. So let me make 4 lines. Choice 1, choice 2, choice 3, and choice 4. When I look at the beginning, my very first choice, there's 10 different toppings I could choose from. So I start with 10. Then, because I picked one, let's say I pick mushrooms, then there's only 9 left for me to choose from. I pick green peppers, and then I have 8 choices left. And then I pick, let's do ham, and then I have 7 choices left, and I'm going to pick bacon. So this is me figuring out how many different arrangements I could have. But I know that using this way, I'm going to end up with different combinations that are the same, right? Because you could picture that I have, let's say I have the ham, peppers, I forget what I said, bacon, and what did I say? Mushrooms? But when I do this mathematical equation here, it means I also could have the peppers, ham, mushroom, bacon. It looks different, but order doesn't matter. So these two things are actually the same. So I want to get rid of all those doubles. So what I'm going to do is I'm actually going to divide by how many different ways I can arrange these 4 things. And the way I can figure out how many different ways I can arrange something is using 4 factorial, because there are 4 choices that I have. And we should know to do 4 factorial, I do 4 times 3 times 2 times 1. Okay? And then you can work out the math on your own. So again, it's kind of tricky, grade 7. You have to really think, what am I trying to find? So on today's lesson, I want you to try it. I've sort of broken down the steps. The first question, you have to solve the same thing 3 different ways. So you hopefully can see where to find these numbers on your division. I should have shown that I had this division bar right here. So do your best with it, but we will do another lesson on it on Monday because it's kind of tricky. So just to summarize, permutation, I want you to think that permutation, think about position. The order matters. Combination, maybe you could think of it this way. Couldn't care less about the order. Okay? So, permutation, we care about the position. Couldn't care less about the order is for the combination. So when you're working with permutations, you actually end up with a lot more options because the position matters. That's like saying with a permutation, it's saying 1, 2, 3 is different than 3, 2, 1. But a combination is like saying me having ham, bacon, and pineapple on my pizza is the same thing as me having pineapple, bacon, and ham, or having ham, pineapple, bacon. So these guys get crossed out because they're repetitive, because we don't care about the order. Okay? And then one more thing is when to use factorials and when to use the fundamental counting principle. I think about factorials when I think about using up choices. So again, think about the popsicles. Think about picking out prizes, right? If I have 4 different prizes for you to choose, the first kid gets 4 choices. The second kid only has 3, and then 2, and then 1. Okay. Whereas the fundamental counting principle is a little bit more like the Subway shop or the ice cream sundae that you're making, right? We could all go to a Subway shop if we wanted. We could all order a cold cut combo on Italian urban cheese in general. Okay. Obviously they could run out, but in general, we could all go and get the same thing. And this just more helps me come up with how many different things there are. So if there's 4 different types of bread, I could do 4. Let's say there's 6 different kinds of sauces. I would do 4 times 6. So this is me coming up with all the different combinations of things, but I'm not running out of an item. Whereas a factorial is when you have limited choices, and once someone chooses it, you cannot choose it after them. Okay? So do your best with the worksheet. You can print it off if you want to work directly on the sheet, or you can just look on your computer and then do the work in your math journal. It's entirely up to you. I hope you have a great long weekend. So I guess I won't review on Monday.